Do you see the presentation? Professor Reddy, do you see this presentation? Not yet.
Not yet, sir.
Okay, now it should come. Okay. You can see it now, right?
Now it has come, sir.
Okay, good. Excellent. Thank you.
చెప్పండి. ఇది లెక్చర్ ఒకటి ఆన్లైన్ ఆనంద్ అని లెక్చర్ ఉంది. లెటర్ ఇవ్వలేదు కదా, అది రిపోర్ట్ ఇవ్వడానికి లెటర్ ఇవ్వలేదు. మనకి ఏమవుతుంది వర్క్ ఇప్పుడు పెట్టలేదు, పెడతాన్నారు మళ్ళీ సార్ నేను ఉండడం. దేనికండి ఈవెన్ ఆల్రెడీ చేశాను కదా అందులో, ఇంకేమడి గారు చేస్తా ఉన్నాను రెడీగా.
ఇది ఒక్కటి యాడ్ చేయండి, తీసుకొచ్చాను సార్.
ఆ డేటా నాకు పెట్టండి.
నేను పెడతాను, మీకు వాట్సాప్ పెడతాను.
సరే అండి. ఓకే.
Sudhan, I think you're upside down, huh?
Sir?
Your picture comes like upside down, huh?
But in my device it is showing all right, sir.
Huh, okay. Interesting, yeah. How are you, Nitin?
Good afternoon, sir. I'm good. How are you?
Good, good, good to see you.
Same here, sir. Same here. So you're in India?
Yeah,
Oh,
for a week now.
okay.
I think I'll present it later. I'm trying to learn. This system is not something I'm used to it, so Satyanan garu, మనం IGC last year we used Zoom, right? It's a step down. Bombay Nathan?
Yes, sir.
Yeah. It's coming clear, much better now, Satyanarayana.
Okay, sir. Okay.
Yeah. Last time we used Zoom, right?
Zoom, sir. But
For the
our university is using this platform for all online activities, sir.
okay.
So that's why we are using it.
Okay.
For IGC, we had Zoom, sir.
Okay. I like this one too. Excellent. New to this, but
We'll wait for 2-3 minutes and start, sir.
yeah, sure.
Now, is it okay, sir? Image?
No, you're upside down now.
Something is.
Yeah, it's correct now. Still upside. I mean, I think your camera setting. Yeah, this is perfect. Yeah, that is correct.
Okay, sir. I'll leave it like this.
Okay.
Sir, we'll start, sir.
Yep, your call. Yep, I'm ready.
So, good afternoon to all of you. On behalf of Department of Civil Engineering, Andhra University College of Engineering, Visakhapatnam, and IGS Visakhapatnam chapter, I welcome you all to this special lecture on problematic soils, geotechnical challenges and solutions by Professor Anand Papala. So, most of you are familiar with Professor Anand Papala. He is popular. He is an active researcher and consultant, presently with Texas A&M University. So, as a formality, I would like to give a brief introduction before he delivers his lecture. So, Dr. Anand J. Papala is currently serving as AP Wiley and Florence Chair of Jackery Civil and Environment Engineering at Texas A&M University, Texas, USA. And he is an Associate Director of Center for Infrastructure Renewal. Both these appointments started in September 2019. He served as Associate Dean, Research in College of Engineering for more than 7 years. And he was a distinguished scholar, professor of Civil Engineering Department at University of Texas at Arlington in Texas, USA from September 1996 to August 2019. Dr. Papala received many teaching and research awards, including 2013 UTA Distinguished Researcher Award and 2010 UT Systems Regents Teaching Award. Dr. Papala was the chair of Soil Mechanics Section, AFS 00 of the Transportation Research Board, and is a new co-chair of new section AKG 00 Geology and Geotechnical Engineering, and a member of Design and Construction Group of Transportation Research Board. He chaired American Society of Civil Engineers, Geotechnical Institute's Engineering, Geology and Site Characterization Committee, and the TRB Committee on Soil and Rock Instrumentation. He is a current member of American Society of Civil Engineers, Geotechnical Institute's Technical Coordination Council. Dr. Papala also served as President of United States Universities Council on Geotechnical Education and Research during the period 2007 to 2009. Dr. Papala has been conducting research on stabilization of expansive soils, UAVs for infrastructure monitoring studies and asset management studies. His research areas also include dam safety, embankment slope studies, in situ intrusive methods for site characterization, infrastructure resilience, and material characterization studies. Dr. Anand has been a recipient of several major research grants totaling over 20 plus millions of dollars from federal, state, and local government agencies. Dr. Papala is the current director of NSF's Industry Institute Cooperative Research Center, site on composites in civil infrastructure at TAMU, Texas. That is TAMU means Texas A&M University. He has been serving as program director of Transit, a university transportation center based in LSU. Dr. Papala's research scholarly record included more than 500 publications, including 220 plus journals, and he has also edited 7 special publications. He has supervised 38 doctoral and 52 master's thesis students, and is currently advising 11 more doctoral students and 2 postdoctoral fellows. Dr. Anand is an editorial member for several major journals in civil engineering, including ASCE Journal of Geotechnical and Geoenvironmental Engineering. Also, he is serving as editorial member of ASTM Geotechnical Testing Journal and edited several books, including 7 ASCE special publications. He has given several keynote and invited talks all over the world, including a prestigious American Society of Civil Engineers Geotechnical Institute's PEC Talk at 2020 Geo Congress meeting held at Minneapolis, Minnesota. So most of you might have watched his PEC lecture on YouTube. So we are very happy to have you here, sir. And we thank you for sparing your valuable time. We know that for a short duration you are on a trip to your native place, but still based on our request, you have allotted some time to share some of your ideas related to problematic soils, because we are in a coastal area, we live with problematic soils. So the topic is very apt. So I invite Professor Anand Bappala to deliver his talk on problematic soil. Please, sir.
Thank you. Thank you, Professor Satyanarayan Reddy. Can you hear me well?
Yes, sir. You're audible, sir.
You're audible? Okay, good. Excellent. So again, I see a lot of good friends. I see Balakumar and I see a lot of my students, everyone here. Except, I'm actually in Vizag, Visakhapatnam. I'm visiting my, family also here, my parents. I'm actually sitting in my parents' home, but I feel like I'm sitting next to the beach in Vizag behind me. That's just an image, okay? But again, I think I was expecting around 20 plus people presentation. So, I don't know what you did. I just see 83 people. That's awesome. I'm really, really honored that you all choose spend your time today to listen to me. I hope you won't be disappointed. I will try to cover a lot of things, and also I will give you some suggestions. I see a lot of young geotechnical engineers in a mixer here, so this is good for me to talk to you. So let me go ahead and share my presentation. Do you all see my presentation?
Yes, sir.
Okay.
It is visible, sir.
It's visible, right? Thank you. This is a new platform for me, so I may ask once in a while. If there is any issue, please don't hesitate to stop me. So please feel free to discuss anytime. So the title, as Dr. Satyanarayan Reddy mentioned, is Problematic Soils and Challenges and Solutions. Some of these things I mentioned in my PEC lecture, and I will go a little bit here also. And I also added a few new things also to this talk. Again, I want to thank Professor Satyanarayan Reddy for making all these arrangements, including his students, and I really appreciate all of them. So this is an approximate agenda that I will follow. Basically talk more on the area where I really do a lot of my research is on expansive soils, and then also sulfate soils, which I think in Satyanarayan Reddy also works in the sulfate soils. Then I'll talk about some of the hazards we are having with these soils, and I'm not going to touch on soft soils, which again, I think if you live in Chennai and Mumbai, that's also part of the thing. That's also a problem soil, but I'm not going to be talking on that one. Then I will be more focusing on expansive soils, which are pretty high in India. So I think this will probably give you some of our experiences over there that will tell you what we are doing, what they are doing, compare it, you have a better picture of the whole thing. And then I talk about some case studies. Then in the end, I want to talk a little bit about coastal soils. This is something we are getting a lot of new research works, so I'm going to spend some time on it. See, one of my students, Nippo, is also on the call. So he's just visiting also just like me, India. So I think, we're all working on these areas now. So I'll talk a little bit about mitigation, but this work is actually ongoing right now, the last 2 bullets. In the end, I will come with some concluding comments. I think many of you know that expansive soils are mostly made of montmorillonite or smectite clay minerals, which is, again, the structure of smectite is seen on the right side. It has you can see here the exchangeable cation here is the water molecules. And this actually kind of hydrates a lot, this kind of mineral. As a result, your thickness between these minerals, 2 to 1, will start expanding, and that will manifest as a swelling on the surface of a ground, and that movement, that swelling, will cause significant damage to the structures built on top. And that includes pavements like roads, dams, embankments, a lot of homes. I'll show you some pictures over there. So how do we know a soil is expansive? Is we always use this simple test that we do, liquid limit, plastic limit, which gives you PI, plasticity index. It's very primitive test. It's it's always kind of a subjective test, but we use them because we have a lot of database in the past, so we still continue. I would say several times it works, but the many times you may miss the real swelling potential. So that's where, it's going to be a problem. So we prefer always to do the real swell testing, measure the swelling of a soil sample in a odometer test, which will give you better understanding of your swell potential than just relying on plasticity index. Later, I'll explain you how the PI-based method can be misleading also. But one important thing is, like you see here on the right side, the montimonite clay mineral, or we call smectite. And that is the one that is, it's a huge amount of specific surface area, high cation exchange capacity. So in addition to montimonite, you have other clay minerals. Two other dominant clay minerals that we have outside montimonite is your illite and also kaolinite. We have halloysite, which is again belongs to kaolinite family. And we also have other types of 4-1 or chloride minerals. But most of the time, if you look at the geotechnical clay mineralogy or clay chemistry, we talk about these three minerals: kaolinite, illite, montimonite. So in the same order, the worst mineral is on the montimonite. The next, slightly better than montimonite is illite, and the best one is kaolinite. So if a clay is made of kaolinite, you generally don't have a lot of swelling, a lot of compressibility issues. But if clays are made of illite and montimonite in particular, you have huge amounts of problem. So these are some of the infrastructure damage you typically see. And most of them are coming from Texas area, because we are sitting right on top of expansive clay soil. So we have a lot of damage here. Road cracks can be this wide. It could be like anywhere like 5 to 7 centimeters, and then it can go up to almost 0.6 meters or even higher. Then you can see sometimes the cracking. Whenever the rain hits this area, the water goes into the cracks and causes huge amount of failures. And you also see in the home foundations, in the basements, and also masonry, you will see significant differential swelling causes huge amounts of cracking, like you see here, the brickwork kind of moved, and then you have huge amounts of distress in your home. We not only have that issue, we also have it sometimes on the walls, particularly this particular wall, which is actually close to my old university. I think, as you can see here, this is the one which, when we had a huge amount of rainfall in a short duration, this whole thing, got soaked under the water, and then water became like a frictionless soil surface. So this whole thing slided on top, and you can see that all these panels kind of broken and then came down, And we also have a lot of areas, MSE walls. Even though behind the wall, you have a non-expansive soil. Behind that, you have a natural clay, which can be expansive. So sometimes this swelling, from the rain can cause movements of the walls. I have seen the walls moving into the roads, causing a lot of buckling of the roads. So this is also another major issue. So we need to understand what type of backfill or what type of natural backfill you have. So if that is expansive, you need to make sure that you have some compressible medium here, so that will absorb the compressible medium, will take the swelling of the back soil. Otherwise, eventually this will go and put it on your movements on your structure, in this case MSE wall, and that can cause huge amounts of failure. And this is also a lot of dams in our region. What you see, this is one of the dams here. On both sides, you have a lot of slope failures. And you see the slope failures are very shallow, superficial slope failures. Sometimes the slope failures take away the roads, like you see here. So this is a common occurrence because our soils are highly shrink swell or expansive soils. So in extreme summer, It's particularly from June to August, we have high amounts of sun, and then also high temperatures. It causes a lot of cracking, and then the rainfalls that goes in will causes this localized failures. And this is a major maintenance for the agency that deals with this managing this infrastructure. So we have, this is a text dot, which is a highway that is along outside Dallas Fort Worth, and these are all the dams in the Dallas Fort Worth. It's a common occurrence of this type of failures. I also want to bring another type of expansive soil problem. This is what we call sulfate-rich soils. So up to now, whatever we talked about is mostly smectite soils. But you may have a good soil, but if the soil contains sulfate, it's called sulfate-rich soil. This also causes a lot of problems. And this has been one of my research. It started with Mitchell's work, which is Jim Mitchell has done this work. And then Dale Hunter done some work in Las Vegas. Then Dallas Little from TAMU and other people are working. And now we are continuing this work for the last 15 years. Been working on different types of sulfate sources. Most of our soils are gypsum. So gypsum is calcium sulfate. We also have sodium sulfate, magnesium sulfate, which are these are the two other types. But majority of the soils in our region have calcium sulfate or gypsum. So the problem with gypsum, this is a very low solubility. It is a slow release of sulfates. It doesn't come quickly. So that means the problem can slowly start happening. It doesn't happen overnight. It takes like several days or several months, depending on how much of a rainfall dissolution is happening. So that is something always an important. The one way you can look at if we have a gypsum or not is gypsum looks like these crystals, almost like a diamond type things. You put the soil against sunshine, it will shine, So this is one way to know that you have gypsum in your soils or not. So if you have this gypsum material, if you stabilize with the lime or cement, they form a compound called ettringite, and that ettringite is actually heaving mineral. So the soil that has not necessarily naturally low expansive, but they will become expansive just because of your chemical treatment working with the sulfates. So that sulfate is like you can see here, this area, a lot of sulfates, white stuff, and then this one here. So when you stabilize the soil with lime or cement, and then the soil starts heaving because of the gypsum, causing some reaction and forming ettringite. You can see some of the pictures here. This is one of the road that is, lifting 2-3 inches, and almost like you would say, almost 8-9 centimeters. That's a huge amount of damage to the road. You can see how the road is damaged, and this is during emulsion. It's not even put the road on top. You also see the lot of pockets of heaving, and it's localized. It's not everywhere. You can see here. There's one here, one here, one here, like that. So this is enough to cause you have to go back and repair the entire road. And this is actually taxiway of a airport. Even this is also probably got this problem. In this area, we found sulfates a very high amount. So basically, this is also a major issue with this thing. So I told you always we use PI to see whether the soil is a high PI, high expansive. But I mentioned in several times the same PI doesn't mean that they're same soils. I show you here, there are two soils. They have similar PI, but later you'll see that both are different. And one soil actually stronger than other soil, even though they have same PI. But if you look at liquid limits, they're different. But unfortunately, we rely on PI, not liquid limit and PI. There is a liquidity index, so there are other types of parameters you can use. But folks simply use PI-based charts or PI-based equations. That is going to give you misleading results. Another side also, we have two soils. It's a similar PI, but look at the liquid limit, plastic limit. They're different. So sometimes you may want to include the liquid index, at least liquid limit information. It will tell you much more about how expansive. If you just rely on the PI, you can get misleading results. But this soil, you will see later, Fort Worth is a bad, even the PI is 29, this is highly expansive. Whereas this soil, that is a brand, it has a 31, but it's a low expansive because you can see liquid limit is low, So don't rely every time on the PI. So that is one of the things. So a couple of my PhD students, almost 15 years back or so, we started working on this fundamental soil chemistry. We looked at the clay minerals. We looked at how the soil inside the porosity. And we also looked at the unsaturated soil properties using the soil water characteristic curve, which is a relationship between your soil suction, and that is very important because most of the expansive soils are in unsaturated conditions. So then we also connected all these things into some swell properties. There have several papers are published on this. I'm not going to talk about them, and we have developed some interesting models combining them. Obviously, using these tests, you have to spend more money to do these tests, but these will provide you better understanding how expansive your soil is. So this is basically from Jim Mitchell's book. If you look at everything can be linked to composition and also environmental conditions. So here is our compositional of soil types. Here is our conditions outside. Together, they result in different swelling patterns, swell behavior. So combining all of them will be a challenging one. So we tried to come up with a very nice framework where we took the soil, and then the soil is actually has a sand and silt, and then these are non-clay. This is clay. Even though there are a lot of other minerals, these are the three dominant minerals we consider: kaolinite, illite, montmorillonite, and we try to explain them in a simple way, doing some chemical analysis using these three methods: cation exchange capacity, specific surface area, total potassium. If you look at this paper by Bhaskar Chituri, it's published in ASC Journal it's 2011, you will understand how to measure this method. Some of you already probably doing this work. So basically, it will three measurements, three unknowns. So you should be able to solve the different clay minerals. Then that will give you approximate, doesn't give you exact, but that's more than enough. Approximate idea of clay mineralogy in a soil will tell you whether you have too much of montmorillonite or a low montmorillonite but high kaolinite. These things will help you on understanding how much swelling you have. So we took this information and we come up with some chemical mineralogy parameter. And you can look into the papers. I'm not going to go explaining everything. It will take some time. So we gave some mineralogy, some factors. Swelling, high swelling, we gave a very high number. Moderate swelling is like a 9. Low swelling is given as 1. So we use these factors. We call it as SF, or swell factor. And we multiplied with this equation to come up with what we call is a chemical mineralogy parameter. And then soil suction, we gave them something called mechanical hydroparameter. This is SWCC. So change in void ratio with respect to soil suction. You can measure this will drive how the flow will happen in the soil, because you need to have moisture flow to induce swelling. And then we come up with something by combining these two. We came up with a mechanical hydrochemical parameter, MHCP. And here is some of our we tested several soils and we measured these parameters and we measured swelling. And there's a good trend. It's not the best high R square, but it's a 0.7 is pretty good for Geotech. So this is one of the ways we actually come up with comparing them. So this paper is published in Engineering Geology. So it's an empirical swelling, how do you model it? Again, if you can measure this, it'll give you a better idea of how good a swelling soil you're dealing with. And we not only measured swelling, strain, we also measured volumetric strain at different confining, like 7 and 50 and 100. So you can see these models we developed has a much more fundamental, the soil behavior is incorporated. So they're much more robust and much more strong, better in my opinion. So we have developed several models. There's another model, we call it a surface area ratio, because how much of surface area is exposed to the moisture. We come up with a TSAR factor. This paper is also published in the ASC Journal of Geotech, and this is Aravind, actually. He was my PhD student, and he worked on this for his PhD. And we came up with another model, and this is also, it's a interesting model, gave pretty good results. So this takes extra work. That means you really have to do more chemistry, soil chemistry work, and also some suction testing. But adding more testing is important if you want to know what type of soils you are dealing with, particularly if a problem soil. So don't try to solve a problem soil design by doing a simple plasticity index testing in the lab. Just take it in this way. If you have a very problematic condition, you want to invest some testing. Don't try to do it, very simple, cheaper technique. So it's almost like I remember Professor Madhav used to say, it's like Geotech is like a health, like a doctor. Same thing. If you want to know what is the problem of a soil, you want to spend little, stronger to good testing. Like sometimes CT scan, that type of testing. We can do like in this case, particularly what you see is a mercury intrusion porosimetry. These are expensive testing, but they can give you better idea of what type of soils you're dealing with, and that will give you better design. You always get this sometimes, we want you not to think in an academic way. We want you to do it a much more simpler way. Don't spend too much. But then when there's a failure, you will be liable. So at least I know in US that is a big issue for us. So we need to be careful. So we want to be doing everything perfectly. We want to test as much as we can, and then use a more engineering judgment to develop our design. So that's why a lot of young members are listening. So try to do a more robust experimental work that will give you better confidence in your problematic nature of your soil. Do not try to do it a simple thing. At this point, I just want to mention, this is the Professor Ralph Peck. I know Balakumar, he mentioned, we talked some time back. He's considered to be like one of the practical mind, great practical person. So this is one of his quote: translating the findings of our research into simple concepts and procedures for the guidance of the practicing engineer, in my opinion, is a duty and worthy activity of profession. So remember, whatever you do, you need to convert that into practice. So don't just write papers and leave it there. Okay, you need to show how it can be implemented into real practice. So this is something is what we call as a translational research. Everything what we do needs to be connected to the design of infrastructure under real sites. Okay, so that is where you really need to spend on this particular topics. So at this point, I'm going to show you a couple of studies that we are doing, on the expansive soils. Some, that will give you a good idea on how we are dealing with them. So this study is about pavement in like roads built on expansive soils, and this is one of the area outside, almost like maybe I'd say 45 kilometers from Dallas area. So typically when we have expansive soils, we use chemical treatments, mostly these materials. And we also use some geosynthetics, like the geocell or geotextiles, different things we use. So these are different methods that are typically practiced. Some works very well, some have issues. But again, one of the things we got a project with the highway agency. They want us to know why in some cases it works, why in some cases it doesn't work. That means if I use chemical treatment in some soils, no issues. Everything works well. There's no issues with the road. It's perfectly uniform. There's no heaving and cracking on the road. Everything works good. But in some cases, it is an issue. So what we did is that is when we did the study, we took all the soils from different parts of the Texas. And each soil, we did identify how much montamonite, intraillite, and kaolinite using our Dr. Chitturi's method, the one he developed with the CEC, specific surface area, and potassium. And we approximately identified them. So the ones that you see the red color font here, like Austin, Fort Worth, Paris, and Foray, you can see these have like montamonite high amounts, close to 50%. This one is 48, but all others have above 50. So the ones that are below are like, we put it as a dark numbers. So what we did is we took this is the one you saw before this slide. So in each case, the soils have similar PI, but when we look at the dominant mineral, like you see here, the previous slide here, they have the kaolinite and montamonite. So we went back and see what is the most highest amount of mineral. So the Bryan soil has a kaolinite, even though it has a PI 31, it has a kaolinite as a dominant mineral. Fort Worth, on the other hand, is 29 with the montamonite. And if you look at the liquid limit, obviously higher the more montamonite you have a high liquid limit. So you can compare these two to know that this soil is not as expansive. Even the PIs are similar. So this is what we are trying to tell you, try to use a little bit of chemistry or chemical testing that will document or provide you better understanding. So using concept of PI and liquid limit also will helpful. So it's the same thing with the Paris and for B, and again, the 36, 37, this soil has a montamonite, whereas this soil has a kaolinite. So the reason why I'm saying these minerals, you will see later the Bryan soil has no problem when I stabilize with lime. Whereas Fort Worth soil, if I stabilize with lime, the moderate dosage, this soil did not perform well in our testing. So this is one of the things if I know the mineralogy, I will understand it. And that explains why in some areas we have premature soil failures, whereas other areas we have no issues. So one of the things we did is we did look at this stabilization design. We tried to look at lime treatment using this chart, looking at the PI number. So we used lime as our stabilization. So here is one of the things we did is we stabilize with lime. There's a simple Eats and Grimms method you can follow. But one important thing we did is once we stabilized them and prepared samples, we tested them for durability. So the durability, we followed the ASTM method, D596, which includes 5 hours under wetting, followed by oven 42 hours. And then each time you go back, and we call it as one cycle. One complete wetting cycle plus drying cycle is considered as one cycle. Okay. So here is our soil that is untreated. This is the Fort Worth soil. So untreated won't survive too much. Within one cycle, the soil started crumbling. You can see this is a wetting. This is during drying. You can see how much shrinking happening, cracks you can see. The minute next time we wet it, it started crumbling. So this is obviously untreated. So there's no strengthening. So there's no way. The same soil, when we treated it with 6% lime, it worked okay up to 10 cycle. So after 10 cycle, it failed. So remember, this is the soil that has a Montemont lime in it. So if your threshold durability cycle is around 21, or even you can establish the number of cycles. So this one didn't even go halfway. It failed before that. So this soil, because of Montemont light, it only worked for a certain time. In the beginning, it performed well. Again, with every time your seasonal changes, within few seasonal changes, you will see sharpen failure. And that is what we learned from this, looking at the mineralogy and then comparing with the durability, we were able to explain what is causing the problem. And here is the data here. And you can see here, this is another soil is called Keller. And this one has kaolinite. So you can see the 21 cycles we did. Yeah, little bit of volume change, not that much compared to the untreated soil. It's a huge amount. Whereas this 21 cycles, the soil performed UCS strength performed adequately, did not even drop the strength. Whereas the Montemont light soils, like this one, Austin soil, the Montemont light, the strength after 21 cycles, it went down to zero, almost to the zero. The same thing here, the sample did not go up to like 21. It failed. This one is around 13 cycles, it failed. So if one thing I want to mention here is if you see there's a cement also. So when we added cement, this actually, the X's are cement treatment. You can see here 6% cement. This one survived all 21 cycles. But when we looked at the strength, how the strength is returning, strength is still going down. It's not really good because you have to see, after durability cycles, you need to at least maintain close to like a 150 PSI in that range. So the strength-wise, it's dropped. Volumetric stability-wise, it is doing okay, but strength is still not good. That means soil is like not expanding, shrinking, or swelling, but it is losing its strength, so it's not good. So, but one interesting thing is lime actually failed within like around 12 plus cycles, whereas cement actually went all the way. One reason is cement provides more unconfined compression strength, so the increase in strength is helpful in reducing the whole thing. So this is summary of all our testing of durability. If you can see here, this is again amount of lime stabilization different times. So everything that soil has a Montemonite as a dominating mineral. If you look at here, the number of cycles it survived, it varied from 4 to 12. So none of these soils, survived our 21 cycle thresholds for durability. The only ones that survived are the one that has kaolinite. So that tells you that, soils that are rich with Montemonite, you really need to do much higher stabilization or even consider other things. Otherwise, you will have some certain swelling problems. So that is one of the things we learned. And then we came up with a modification, check the Montemonite amount by doing some chemical analysis. If you do have, too much of Montemonite, okay, particularly this one, try to increase your dosage, add more chemical dosage. That's not necessarily a good sustainable solution, but you have to increase your strength so the soil won't collapse very rapidly. So this is one of the things that we tell them. You have so many roads that fail, so many, many countries have this issue. They just use thumb rule, this PI, this one, go with the 6% lime. In many cases, it works because there maybe the soil is not necessarily rich with the montamonite. But many places, where it's too much of montamonite, that 6% lime, thumb rule doesn't work. You have premature failures. So when you have this forensic type of investigation, you will know what is the issue. So that is one thing I want you to do. If you ever see any road that failed, particularly stabilized area, that means there may be a clay mineralogy issue. So that is something you may want to do. The second case study I want to mention a little bit is more about sulfate soils, high gypsum, you can see. So when they react with the calcium, lime, and cement, they will form this mineral called a Tringite. So this is a Tringite. It looks like a needle-like structures, and this is what it is. If you can see the shape, it will looks like an hexagonal shape, like on the long needle shape structures. So this is a chemical reaction. So you have your lime reaction. This is your lime, hydration of lime. It releases calcium. And then you have the soil. Whenever you put lime treatment, your pH will start going up. At high pH, your soil starts releasing alumina and silica. Many times these are good things because these are the ones that form your pozzolanic reactivity compounds. But unfortunately, in this sulfate soils, these things you can see in the last equation down here. So if you see here, you have calcium from lime, alumina from soil coming from here, this area. Then you have sulfates in the soil. And then all of these three, in the presence of water, will produce this long equation here. This is nothing but a Tringite. This Tringite swells, it bulks up 2 times its volume. So anytime you give water, it becomes like a sponge, like it almost like swells so much. So a soil that is rich with sulfates, when you stabilize with lime, typically lime is supposed to suppress swelling, but instead of suppressing, it actually compounds the problem. That is one thing I would like you to know, that this is an issue. So we have been working on this for several years now. I have documented all the various case studies. Many places we found out a Tringite is a big issue. And then the other thing is, in some cases, it happens within weeks to months, and some cases it takes years. The reason for that is I just told you, gypsum is a low solubility. Sometimes if there's too much rain or water, if it's dry, it doesn't release. But if you have too much rain, that's when it starts coming out. Gypsum produces sulfates. So that is what needed. And once you form the Tringite, you need to form more and more. It needs to grow. Then only you will feel this heaving. Suddenly, like some cases, 6 months, or sometimes it takes a year, sometimes several years, then suddenly you start seeing this, a Tringite attack, we call it a Tringite-induced heaving, or also known as sulfate-induced heaving. So we are being very well known in this area. We have published quite a bit in this topic. I divide them into 2 types. One is low sulfates, moderate sulfates, I would say 8,000 or less. Sulfates are more than 8,000. So this one, we have done a lot of studies all over the world, different materials like double liming, fly ash. All these things have provided some good results. Some of them have stopped it, but then after a while it stopped showing up. But we have good information on what works for these levels of sulfates. The ones we don't know is this high sulfates. When you have more than 8,000, unfortunately, a lot of soil areas in our region has high sulfates, up to 20, 30,000 parts per million. So this is one thing we have done a lot of studies. These are all our agencies that funded our projects. So this is more than 8,000. So we did like 6 different soils. You can see the sulfate levels. Some of them has a lower sulfate, but we spiked by adding gypsum. So that way we got more than 8,000. So we added extra for these 2 soils and this one also. So we have increased our sulfate levels. And each case we tried lime and then also 6% dosage, and then we tried different things. One way we try to do is each time when we tested it, we try to do different mellowing. So what is a mellowing? A mellowing is initially when you mix with lime and the soil, you mix everything and then you leave it for certain time. Typically they do it for 24 days or like anywhere between 0 to 24 hours, so that is like 1 day. But what we did is we wanted to leave it for 3 days and 7 days, and then we come back and mix it and then compact the samples and test it for swelling. So here you see the 3 mellowing periods we studied. One is 0 day, which is immediately, and then 3 days, 7 days, this extra mellowing. What happens is during 3 days, 7 days, the Tringite forms, but we go back and recompact them. We mix them with again, and then we compact them. So here you can see the 0-day much high swelling, but with the increase in mellowing, the swelling starts subsiding. So this is one of the treatments or one of the methods we do in the field. When we stabilize the lime, we keep them for 3 days. Contractors do not like it. They like to do it everything within a day or two. But if you have sulfates, you have to wait for some time. This is one of the things we learn. Mellowing can reduce it, but it can only work up to certain amounts. But if sulfates are going up to above 30,000, we found that's going to be still a problem, as you can see here. I think there's always a limit. So anything above 30,000 parts per million, you need to remove some sulfates from the soil and stabilize it. Otherwise, there will be a problem and they will always cause a lot of issues. So this is one of the things we learned from this study. We showed them, any soil that is below 30,000, no problem. But if it causes more than 30,000, we have an issue with our soil sulfate reactions and causing more heaving. And we even studied this in a field. This is one of the section close to almost like 80, 90 miles from where our old university is in Arlington, UT Arlington. That's where our students did some work. These are test sections. We prepared them with the different fly ashes, mellowing, and we monitored and we found out the increase in mellowing are reducing lime and adding some fly ash actually helped in reducing sulfate attack. Okay, so there are ways you can do it. So this is one of the sulfate soil study we have done. So this is in the field. We prepared one, as I mentioned, lime plus fly ash, and this is the section with the extended mellowing. This is our students actually collecting data in the field. We are monitoring the heaving on the highway. This is construction pictures. You can see here, this is the UT Arlington picture here. That's where this work was done at that time. And we have collected a huge amount of data. And basically, this was a very successful project. We have shown this, how we can stabilize high sulfate above 8,000 up to 25,000. Anything above 30,000, we have to come up with new thing. Fortunately, those we don't encounter that type of sulfates, very high sulfate soils. Too many. We try at this time remove it and remove the sulfate pockets. If they are pocket, they're not everywhere, so you can do that. So I'm going to move to the final topic for you, and this is where, as I said, I'm from Vizag. I live next to the beach, so. And again, coastal is something where coastal environment is causing a lot of issues these days because of increase in due to climate change or different regions. We're having a lot of more rainfall events, more flooding, more hurricanes, and more typhoons. Just name it, everything is happening, and you can see. So a lot of these things, as you see, even in Vizag recently, huge amount of rainfall causes a lot of erosion. I seen recently also a lot of this erosion takes away sometimes the roads or sometimes even the buildings that are placed next to it. And these are some of the pictures in US. You can see the whole pavement next to the beach area during the flooding. It kind of damaged everything here. And again, they try to do different breakwater systems to energy dissipators. But again, this works, but these are expensive. And there are some places you have overtopping. And sometimes the homes that have deep foundations, we have a lot of scour like this. And that causes the structure, like the homes, they may collapse. So these are all kinds of built environment issues. So we've been working on this topic. We were recently funded with National Science Foundation, NSF. Maria, she's a faculty member in our department. She is actually lead on this project, NSF funded research hub, to study how to increase the resilience in underrepresented coastal communities. So if you look at, this is Texas, and this is Louisiana, Mississippi, Florida. So all these regions, we get a lot of in a coastal region, communities are impacted by these hurricanes and flooding and erosion issues. So we were trying to come up with a way to increase the resiliency of infrastructure. So this is a major project for us. It's around $4.2 million NSF funding. I'm working on the geotechnical aspects of this project. And as one of my students here, Mani, put all this information here. We identified several types of issues, particularly sea level raises, that is increased level of flooding and erosion. Plus, seawater can intrude the salt water into the soil. It's also a major issues, and subsidence, we know that is another major issue, particularly in outer harbors. And then flooding is a major thing, type of flooding and the wave loading, and all those, particularly during the storm, the amount of force that is coming and acting is important. And some soils can stay, some soils are not going to stay. The ones that are low unconfined compression strength can be easily erodible. So erosion and scour is a big issue in our pavements and also built homes there. Okay, and as I mentioned, the wave action and the loading is important. And this also indirectly connected to all of these erosion issues and also sea level rise issues. So just show you a little bit about the ones we are working on pavements. Anytime you have a highway pavements here, okay, if this is a typical pavement, coastal pavement, you have waves coming and then flooding, and then you have homes and everything built here. So we want to see what type of things we have to monitor and what kind of designs we need to do. So this particular subgrade and base layers will support during the flooding and during the sea level raises. It will provide very good thing. So one of the things we are looking for pavements, we're looking at the performance of the pavements using some non-destructive testings like LWD, lightweight deflectometer, falling weight deflectometers, and profilers. And we want to check this pavement parameters with time and see different types of treatments we're doing. And some of them are nature-based techniques, some of them are stabilizing with the cement and other types of things. All these things will provide a very good resiliency, means a stronger pavement without being subjected to the failure. So we are trying to look at different types of treatment methods, adaptation strategies. And one of the things I want to mention is protect these structures. So you can do if you have roads next to the beaches, you can what do you have to do so to protect the damage? You can do it during flooding. You can do it with when the normal conditions. Normal conditions generally they're safe, but the worst case scenario is when you have flooding coming from a cyclone event or a hurricane event, whatever it is. That's when you need to come up with a method. So there are different things that we study nowadays. A lot of people use hard revetments, use a sea walls. Like in some areas in Florida, they built a sea walls, so the sea level ranges will be will not let the water to go to the other side where the infrastructure is. So they try to protect them. Some kind of hard revetments also they do. And some people use soft technology, soft engineering solution. They're more like what we call as a wetlands. They use marshes and they use different types of natural solutions. They're also providing very good effective engineering solutions. So these are what we call this is protecting our infrastructure from getting damaged. And there's a lot of work going on in these solutions. And this is something we have been working quite a bit now. And we also like to say accommodate something. That means elevate infrastructure above flood level. That means if we know where the highest flood level, we want to raise that infrastructure by maybe a pile foundations or something. So we raise the elevation of your slab, or the floor. So this is something is very common nowadays in the areas. And if you are using roads in that area, we want to use drainable soils, materials like reclaimed materials that will provide a drainage. So there's no prolonged flooding and then those things. And we are looking at them. And one thing I also want to mention is all these technologies nowadays use a lot of geosynthetics, particularly geocells and geogrids. They will also provide a lot of treatment, what we call as a stabilized sections. And we actually have a couple of test sections we are interested in monitoring for another project. The worst case scenario is really this case when these things work, just to remove that area, don't build anything, but this is not the best area. So there's a way you can do what is called NNBF, it's called nature and nature-based features. If you can build some kind of what I would call it as a marshes or wetland, you can reduce the energy dissipation into this area so it doesn't come to the road, doesn't come to the home that is next to the beach. Okay, so many places in Kakinada and Vizag, and I'm talking more on East Coast where I am from, but I'm pretty sure this is same in Mumbai and other region, Kerala. And in fact, the next IGC, I'll be working with the IGC Kerala folks. We're doing like an Indo-US workshop on on this coastal corridor. How do we come up with reducing the damages coming from coastal flooding? So that's the topic I'll be. Please stay tuned to that one. It's going to be in next December in Kerala. Hopefully, it's in person. So this picture, I just took it day before yesterday. I was going to one of the locations there. I just really liked it because, this is the area I was told has a lot of erosion. You can see the material washed out. Of course, this is one of the oldest technique, but it works, reasonably. You can see this is the tree, like what we call it, shrubs. Like, they were like using the things and they put one end to other end. They put the soil and then they compacted it. And you can see these things are going all the way on the other side. So this is like, a long sticks with sometimes vegetation. This provides a temporary relief without any issues. And again, it's a simple and cost effective. You can go back and repair it. Again, these things were done in the past and we're still doing it also. I think, with the geosynthetics, of course, more costly, but this is something we've been doing it. And I think, I like this thing because this is where like ideas will generate. We know, I think a lot of what we call is a jute type of reinforcement technologies, other things to cut down the erosion issues. This is something we have been doing it. Again, these guys who are doing are not necessarily engineers, but they know what works. So we can learn from them. This is what we call is a natural solution. One can learn from each other. So, and also very cost effective. Even if it washes out in the next rain, they can go back and, put it very quickly. Whereas if it's a geotextile or a geograde, it's something more costly, but of course it probably won't fail. But that is something we have been, looking at it. So the coastal soils and stabilization of them is very hot area right now. And I think it's because, we are seeing increasing intensities of hurricanes and cyclones and all kinds of them. Then the amount of flooding is becoming huge. I mean, it's not about, definitely we know that part of the climate change is, doing it. Sea level rise is an issue. We already recognize that. So, and also salts coming from coastal water, intruding into the soil. Salt intruded soils are not good for stabilizing. They actually don't work very well. So, and then prolonged exposure of flooding that causes soil softening. So we were looking at all these things causing a lot of problems, not only to the roads and bridges, also for the homes that are close to the coastal line. So there are ways we can stabilize them. So this is one of the areas we are working now, geopolymer treating some sandy soils. We have been working on the coastal sandy soils on this for our US Department of Transportation. We also are interested in breakwater foundation systems with geosynthetics. We are working at this topic from our NSF site that we have. And I just mentioned the new project. And one of my PhD students is working on how do we increase the resiliency of the built infrastructure. And we are studying fundamental causes of the problem, plus we're also looking at some adaptive mitigation measures. So together we're coming up with a holistic picture and also using some new things. This is something I would like you to Google this one, nature-based features. On the Geotech side, you will find some wonderful reports on online and the Google. I would suggest you to start reading it. This is a hot area right now for research-wise. There are a lot of like dunes, marshes. Everybody's building them to, these are very cheaper solutions, but they can reduce the damage coming to the infrastructure. These things will absorb all the intensity of the waves, the wave forces, and also the flooding. Everything will be taken by these nature-based features. So it won't affect the structure that is built behind that area. So with that, again, as I mentioned, the problematic soils that I touched today, mostly I would say expansive and also coastal soils. Expansive soils are natural or man-made. And one thing is, important thing is understand what causes the expansive behavior, clay mineralogy. And the important thing is when you design a solution, use a better durability methods. Like once we showed you 21 cycles, some durability. It takes longer time to design them in the lab, and that is what I think we needed before doing it prematurely and then go to the site and put something, and then within a month it fails. Within a month or so, it will fail, and then you have this issue. So you need to really look at the natural, the way you stabilize natural expansive soils, use the durability. Sulfate soils already mentioned, like different types of sulfate soils. There are already some good work going on from Satyanarayana and others do it. But younger guys, they look at the coastal soils, and there's a lot of issues that are happening, and there's a huge amount of research is happening. Many countries are already investing. So this is something because we have such a huge area of coastal along East Coast and West Coast. This is an area I hope we're already doing some work, and I think we can do more. Okay. So everything what we do, we need to develop solutions that should go into the field implementation. Do not just stop them at the lab or some kind of simple experimental work and that's it. That is not sufficient. You need to demonstrate that they work well in the field. Without validation, they will not be embraced by the practicing community. So that is why we need case studies. That's where I would like to mention. So let me again acknowledge Satyanarayana Reddy, Professor Satyanarayana Reddy, good friend. He's, thanks for, it takes a lot of effort to put together. I couldn't say, I was really happy because, and again, it's after 2 years back, last year we're supposed to have a big IGC in Vizag. I missed that one. We had an online event. Hopefully something in the future, would like to, I would like to see like, more and more events, hopefully in a coastal area. So that would be helpful for understanding coastal issues. I know there are a lot of good, interesting work. More can be done. And again, IGC chapter also, Vizag IGC chapter, I want to thank them for their support. And the work is not done without these guys. These are my team. I only put a few people. There are much more than that. Again, I just want to mention Congress. He works as a postdoc, and Ashraf, he just graduated. Ashraf is my postdoc also. Saintan is a professor at BITS Pilani. He is happily settling in BITS Pilani. Tejo is from Vizag. He's actually here. Today went to Tirupati, I was told. So he's flying this morning. And Aritra is also, works at South Dakota University. So these are some of my students working. Their data was using in my presentation. I also want to mention 3 students who are actually all from India. They're all in India. They're just visiting after 2 years. Nipo, I know he's in the outside in the group. Prince also, and RK Krishna Ashwar, he's just, I think he just came to Hyderabad. If you want to know more about our group, you can find that information over there. So these are funding agencies. These are all the people. This is our campus, beautiful campus. So again, that basically tells these are all the people who do all the work. You might recognize some people. There are a few people here, like, I see Prince is here and a few others. Without them, my work is not complete, and they are the ones who do all the hard work. But with that, I would like to answer if there are any questions. I'm happy to answer any of the questions you have.
Good evening, sir.
Good evening.
Sir, I am Sandhya from IIT Madras. I am a research scholar here. I have one question. Generally, in literatures, they mention that after 5 cycles of wet-dry cycles, the soil attains equilibrium stage. So you have mentioned it is required to go for 21 cycles. Can you comment on this, sir?
I think in the literature that probably is done for that particular soil. I don't think you can generalize that, that it's going to happen to every soil. The soils are not everywhere same. So you need to study every soil as they are. And you will be surprised to see that, that 5 cycles is not sufficient. In many times, you need a lot more than that, So that is something, please be open to that thing. I know maybe again, the study, whatever they have done, that they have found 5 valid for that soil, but that's not applicable for everything. Soils are so different from one another. Good question. Thank you, Sandhya. I'm from IIT Madras too. I did my master's over there.
Great, sir. Then one more small question, sir. While for stabilizing sulfate soils, can we go for sulfate resistant cement? Because one of my senior has done a research in this. He has was working in sulfate soils, and he has stabilized using sulfate resistant cement. Can we go for like that, or it is okay for a normal Portland cement itself?
So that's a very good question. Let me tell you this. Sulfate, high sulfate resistant, like a type 2 or type 5 cement, mostly we use it for concrete. Okay. We did study with, these for stabilization also. So if you know what is type 2, type 5 means they have low calcium, okay, low alumina. This is what they have. I mean, like if you look at the chemical composition, they're different. They're supposed to reduce the concrete side attack. They can work in type 5. In one of our studies, we used type 5 for cement treatment of the soil. It worked well because it did not produce, because it has a low amounts of calcium and low amounts of alumina, so that's why Tringite amounts are smaller. So it worked well. So, but these are very expensive compared to the traditional ordinary Portland type 1 cement. So it could work, but again, they're more meant for like pile foundations where you sulfate. The next to pile foundation, you have sulfates that attack the concrete. That's a different type of issue. Okay. So whereas sulfate heaving is a Tringite, and the Tringite is swelling because of water, it's a little different one. Okay.
Thank you, sir.
Right.
Hello, good evening.
Good evening, Anil.
Yeah, good evening, sir. Good evening.
I don't know who asked me the
question for you.
Okay,
Yeah.
go ahead.
Yeah. Sir, in this sort of soil where we have, what is the possibility of going for deep soil mixing? That is to 70 shallow mixing, but mixing throughout the length. So if we make a system to improve upon, what will be the behavior in that? And congratulations for the excellent talk. Quite very informative.
Oh, thank you. Thank you. I'm glad you asked me about, let me just show you. I have probably like a published, what we call it, like, let me just show you quickly. I'm going to share it. So if you go to the ASC Journal of Geotechnical Engineering, Anil, like, particularly, let me just show you. Okay. Yep. Let me share the screen quickly. And I think, yeah, this is it. I'm going to share the screen. So I think that that's a very interesting question, and also a very excellent question, because you may want to look at, I don't know if you can see the screen of the Journal of Geotech. Can you see the screen?
Yes, sir, we can see that. Yeah.
Okay, this is good. So you asked me about deep mixing, deep soil mixing and stabilization. This is the first paper of January 2022 in the ASC Journal of Geotech. Okay, so this student is Raja Majanapur. Actually, he's from Vizag too, and it's surprising. So this guy actually he works in Houston. We have 3 papers in this journal on the deep mixing. We are the first ones studied the basically the stabilizing this expansive soils using deep soil mixing. It actually works well, but one important thing is the big difference between soft soil and expansive. Soft soil, everything, like settles down, right? So you have what we call the arching when you place a grid, geogrid. Whereas swelling soil, it will swell between the treated soils will stop swelling. In between, you have untreated that will swell. So in order for them, you need some anchoring that needs to go into the reinforcement mat within the area. So if you look at the paper, it will show you how do you stabilize it. But you could do it. In fact, the method we developed, there are a lot of Sweden is one of the best in the deep mixing. Actually, they implemented in Middle East. There are areas in Middle East that have swelling soils, expansive soils. Oman and Saudi also has some expansive soil. So it's a slightly different thing, but we did this study in Texas. We have one area has 15 feet, not too deep. 15 feet is not too deep, but we almost 5 meters. But we sure we can do stabilizing with the deep mixing for such a deep, because the other option they have is remove 15 feet of soil, which is huge amount of soil. Where do they going to dump them? And this is a highway project. So yes, I think you can do deep soil mixing with a different slight of design. You should be able to do that.
Thank you very much. Thank you very much for this thing. And exactly the same process, because we don't have to go that deep, because it's that 15 feet or 20 feet, which is the governing criteria, especially for the road structures. Yeah. Thank you very much. That was
exactly. That's a very good point you mentioned. The reason is the expansive swelling behavior. This is something I always tell this to my students. As you go down in the ground, swelling will start subsiding. The confinement will start impacting on the soil. So it will suppress your swelling. So most of the active depths of the clays are anywhere from, I would say, 5 to 12 feet or 15 feet. Anything beyond that, you won't see that much of the felt at the surface level.
Yeah. Thank you. Thank you very much.
Sir, I got one small question, sir.
Sure, Bala.
Hi, I'm Dr. Balakumar here. Hello, am I
Yeah,
audible?
I can hear you.
Yeah. Now, what I would like to know is that see, we all talk of clay mineralogy, clay structure, and things like that. Now, when you are now trying to install a pile group into the expansive soil at the top portions, 5 meter or 6 meter. Now, what will be the behavior when it is subjected to a lateral load, as well as the cap soil pile interaction? How to assess that?
So you're talking about soil structure interaction issue. This is slightly different. So it's not something. So if you give a exact soil composition and then soil properties, yeah, definitely. This has been like one of our earlier projects. It's an interesting project. Actually, it's published in ASTM journal. We have a shallow foundations in an expansive soil, and this happened. All the foundations came uprooted because we have an extreme winter in February, March timeframe, and after rainfall. So we have a rainfall event, then soil started freezing, then everything like started swelling, and then pushed the piles up, and everything came out. So we kind of know that the depths of the foundations are not sufficient to take the beyond the non-swelling lengths. So yeah, I think what you mentioned is, I think, Balakumar, I think it's really, I think, can be doable if you get the full distribution of the pressures and whatever the disruptive forces versus your stabilizing forces, you should be able to come up with a more appropriate foundation design for that case. So in that study, what we did is, I can just give you quickly. We tested several piles. We put everything and then we uplifted. We tried to use an anchor and we lifted them. When we came up with what is the length at which you have to go beyond, because you may have like 5 to 7 feet soil that may be swelling, so that won't be providing any resistance. So below that is only providing resistance. So we were trying to come up with what is the case, given diameter, how much I need to put embedment so that it will stay without getting moved out or causing a lot of stability issues. Yeah, I think it takes like a little bit of a more, in addition to getting a better soil characterization, you also need some finite element modeling to come up with a better design for that. It's a good question.
Yeah.
Thank you, Bala.
Thank you very much, sir. Thank you.
Professor, I
Yeah.
would like to ask one small question. I am Ramu from IIT Hyderabad. I work with Professor Shri Shoma and M.R. Madhav. And I enjoyed your lecture. It's really informative. And since it's a payment-related issues also you have addressed, I would like to take one suggestion from you probably. So I work on geosynthetic reinforced payments. So I am more of interested in geosynthetic related things. Say, for example, geocell, I could use, say, for example, I reinforce at the sub-base interface, or like especially for the sub-base interface to the near the subgrade, so that I could control the swelling characteristics at this or heaving characteristics at the top of the pavement. I have this strong opinion that the geocell would resist these crack levels since I'm reinforcing this at the subgrade level. Could you comment, Professor, on this? Like, I would love to take your suggestion.
The interesting thing, Ramu, before I'm going back, I'm going to be at IIT Hyderabad. I'll be meeting with Suresh, actually. Okay.
Sure,
So maybe at that time, I'm going to share you some. Ashraf, I just mentioned, Ashraf did this design of geocells. You may have seen his papers published also. So what we did is also the same thing, but we don't have sub-base. We only have base and subgrade. So subgrade is expansive subgrade. So what we did is in a geocell, I think we used a kind of a wrap material, which is a recycled material. We use them, but we also have sections which don't have that like the geocell. But definitely, as you said, geocells have a high tensile strength. They actually work as a kind of what we call is a crack barriers. So they stop the cracking coming from bottom up, from expansive soil. They actually absorb it so it doesn't show up any cracking at the surface. We have control sections where we didn't use geocells. We have actually documented some movements in that area, whereas on the areas where we did geocell sections, we have pretty uniform, stable uniform. I mean, we have a few cracks, smaller cracks on the geocell section. I'm not going to say everything's perfect, but it worked very well. And like as you said, the geocells are made of geosynthetics that have a high graft strength, and that will provide a lot of times on a heaving soil significant resistance for cracks not to go up. They will stop the crack. In fact, a lot of times in the past, we used as what we call is a stress absorbing membrane, geosynthetics, SAM. So that is one of the things. Geocells, even though they're not like a layer, they're more like a cellular. They can also provide similar confinement effect that can reduce the crack propagation.
Sure. Thank you very much. Yeah.
Thanks, Ramu.
Sir, I got one more question to ask you.
Already?
Yeah. See, the question is, my thing is that when you are installing the pile through the expansive stator, now will the installation effect, will it disturb the clay structure and is it going to alter the properties or not? Particularly through expansive soil, because large areas on the upper level, they play a very big role in the lateral load and things like that, and the way cap interaction.
I think, there will be some disturbance because compared to a natural state versus remolded state, because you are doing the disturbance by maybe drilling through that area, there will be some disturbance, but that doesn't completely alter that, make them non-expansive. Okay, so if the soil is let's say 10% swelling type, maybe you'll get probably 7%. Still is a swelling, so you will see some suppression of swelling, but it won't be completely non-swelling type. So that is the thing we saw. I mean, they can't change their color. They still have the smectite in it, right? So that is one of the issues with them. I mean, it's an interesting. Sometime back it was some folks actually said, if we grind the clays that have already, smectite is a very, very fine clay mineral. What can you do? You can't grind any more further. Smectite is the finest of all the clay minerals. So you can't really change them. They're still going to be there. But because of the remoldness, or because of some, like as you said, some fabric changes may happen also, they will be not as expensive as they are in the natural state. So,
yeah, that's right.
So nice to see you, Dr. Balakumar.
Thank you, sir. Thanks.
Always pleasure.
Yeah.
So, any other questions, guys? I'm just going to leave that to Dr. Satyanarayana already.
So if there are no questions, I thank you very much, sir, for your highly informative and interesting talk with case studies, and for giving a complete picture of expansive soil. You have touched the most important soil chemistry behind its swelling mechanism, and various stabilization methods, and you have touched upon even deep mixing of expansive soil as well. Till now, people are used to think about deep mixing only for soft clays. So with your information, now people can even try to do deep mixing into expansive soil to alter its behavior. Particularly useful in highway projects. So thank you very much, sir. Not only that, you have given elaborative and clear explanations for all the queries raised by the participants. Very good points were brought out of the discussion. I hope all of you have enjoyed the lecture of Professor Anand Pappala. So I take this opportunity to thank the senior geotechnical professionals in the country like Balakumar, and leading geostructural consultant Dr. Anil. Of course, Dr. Neelima was also there. She left due to her work.
Yeah.
Not only that, I may not be able to address all. So thank you all for taking interest in this event. And we continue to organize events of important geotechnical importance in the days to come. So on behalf of Department of Civil Engineering, Andhra University College of Engineering, and IGS Visakhapatnam chapter, I thank you very much for your participation and making this special lecture a grand success.
Oh,
so thank you.
Thank you, Satyanarayana. Thank you. I just see one of my former student, Raja, also there. So it's good to know everybody there. So thank you. It's a wonderful thing. I'd like to see a face-to-face presentation, hopefully very soon next year. Maybe at Anil at your conference, right? IGC.
Yeah, sure. We all will see each other in the next conference.
Yeah, I hope so. I mean, I missed it in Vizag.
Yeah.
I didn't go this year, but I think it's really wonderful to have face-to-face to see all these great, wonderful folks, students.
Maybe we'll back to normalcy with IGC 23 Kochi event.
Yeah.
That's what I was saying. 22, right?
22. Yeah.
Yeah, 22, 23 Roorkee, yeah, 22.
Yeah, thank you, Satyanarayan, for organizing this. It was very informative and knowledgeable. And good evening, Balakumar sir.
Good evening, sir. See, yesterday we were attending the IGC conference. There had been a lot of papers on soil stabilization and the ground improvement. These two are now getting mixed up. See, many of the stabilization papers are becoming what you call that ground improvement. And most of the papers, one thing funny which I have seen is none of them have touched on clay mineralogy. They were only trying to say that the liquid limit, plastic limit, plasticity index, and what is the mechanism behind trying the stabilization, or what is the mechanism behind improving that property. That had never been discussed in that. That is one thing which is lacking here. Sorry, extremely sorry.
No, it's okay.
See, that is one thing which I found that it is lacking. But after listening to this type of lectures, it really throws a lot of light that the clay mineralogy should revive back. When I was a student, they had prescribed me the book on clay mineralogy by Grimm. That is a book which we are using in our fundamental first year soil master's level. But now today, the clay mineralogy subject itself, I'm not seeing anywhere. Most of the times it is only with reference to the adding the materials and reducing the properties. How the property is reduced, there is no answer.
I mean, I think, in my opinion, we have so many advanced, like a lot of folks are doing great work from India. So I think I agree with you, Balkumar. There are some things we can help, because I know, clay mineralogy is not an easy subject for many, because particularly if you have a chemistry background, if you don't have it. But I think, this is where I am fortunate. One of the things we do is we work with chemistry department folks. Hopefully that is something down the line when I meet with some of the faculty here, because there's some areas that I can't understand. Some of them are not my cup of my tea. So that's where we need to have collaboration with the chemistry department people, and those can add it. A lot of SEMs and all. In the beginning of my thing, I have a material science people helping me. So that's where I think we like to see. It's still difficult because engineering schools don't have all the they have, but they may not have same interest. But I think it is coming. In my opinion, there's some very good work coming from. I know a few people, they're already doing it. I agree with you. I think it's just liquid limit plastic paper. A lot of the journals don't even look at it. Because there's so many papers on that topic. They want something new and novelty. So again, I see that Srivalsa is also there. Okay, so pleasure meeting everyone, guys. So
thank you, sir.
Thank you again. You made my day. I was expecting 20, 30 people. Satyanarayan, I don't know what you did. You got 70 people. So I was really pleased. So such a nice turnout today. Hey, how are you, Srivalsa? I can't hear you. We had to unmute. I think it's muted. So
Yeah, some connection problem.
yeah. Don't worry, Srivalsa. We will chat through the chat, okay? Oh, okay, I got you. Mike has issues. Okay. Yep. Nice seeing you. And again, everyone, is really, really pleasure. And then thank you, everyone. Thanks for everything. And I'm with my parents. I need to spend more time with them. Okay. Thank you, guys, everyone. Take care.
Thank you very much, sir. Thank you all.
I'll see you soon. Okay. Take care.